In the 1930s, mathematicians dreamed of a machine that could solve any well-defined problem. Feed it a mathematical statement, and it would grind away until it produced an answer. True or false, provable or disprovable. Alan Turing, a young British mathematician, took this dream seriously, but to build such a machine, he first had to define precisely what a machine that computes even means. What he invented in 1936 would become the theoretical foundation of every computer ever built, and what he discovered would be just as devastating as Gödel's theorem 5 years earlier. Turing imagined the simplest possible machine that could nonetheless compute anything computable. It has 3 parts: an infinite tape divided into squares, each containing a symbol, a read-write head that can move left or right along the tape, and a set of rules, a finite table of instructions that tells the head what to do at each step. That's it. No processor, no memory chips, no operating system, just tape, a head, and a table of rules. Yet Turing proved this toy machine is as powerful as any computer that has ever been or ever will be built. If a problem is computable at all, a Turing machine can compute it. The question became, which problems are computable? Here is one of the most natural questions you could ask about a computer program. Will it stop? Write any program. Run it. Does it eventually finish and give you an answer? Or does it loop forever, spinning endlessly, never reaching the end? This seems like something another program could check. Write a master program. Call it halt. That takes any program and its input, and tells you, this program will halt, or this program will run forever. Turing proved no such halt program can exist. The proof is breathtakingly simple. Suppose halt exists. Build a new program. Call it trouble. That takes any program as input, calls halt on it, and then does the opposite of whatever halt predicts. If halt says you'll halt, trouble loops forever. If halt says you'll loop forever, trouble halts. Now ask, what happens when you run trouble on itself? If trouble halts, halt predicted it would halt, so trouble loops forever. Contradiction. If trouble loops forever, halt predicted that, so trouble halts. Contradiction. Halt cannot exist. The halting problem is undecidable. This is not a coincidence. The halting problem and Gödel's incompleteness theorems are the same discovery, wearing different clothes. Gödel built a mathematical statement that refers to itself. This statement cannot be proved. Turing built a program that refers to itself. Trouble running on itself. Both arguments use self-reference to create an inescapable contradiction. Both show that certain systems, formal logic, universal computation, contain questions they cannot answer from the inside. In fact, you can prove the halting problem is undecidable directly from Gödel's theorem. And you can derive Gödel's theorem from the undecidability of halting. They are, at the deepest level, the same wall.